All right, let's tackle problem number 6 here. It says the same car toots the same horn at the same speed and temperature. Now this is in reference to question number 4. So we know the car is traveling to the right at 31 meters per second, and the frequency of the horn is 297 hertz, and the temperature of the air is 21.5 degrees Celsius. So there's what is the question we're trying to solve? What would the frequency of the observer here, what frequency would an observer hear if the observer is moving to the right at 20 meters per second? So the observer is moving to the right and the car is moving to the right, and the car is honking its horn, which creates this sound wave, which is traveling at a certain speed. Now I solved for the speed up here, and I got 343.8 meters per second. Okay. Now, if neither the car nor the observer were moving, right, then the frequency observed by the observer would just be 297 hertz. 297 hertz. But the bottom line is, because they're both moving, it throws off the frequency. So the equation we have to use is this monster over here. And you can look at it in terms of 3 parts. So this is the frequency of the sound, which is 297 hertz, right? Then we have this second component right here and a third component right here. So the second component is a factor that's going to be greater than or less than 1, depending on whether or not the observer is moving. And the observer is moving, right? Because the observer is moving 20 meters per second to the right. What does that do? That kind of, it's like he's running away. The observer is running away from those sound waves. Even though the sound waves travel really fast, the fact the observer is running away from them means they're going to hit the observer less frequently, and that's going to decrease the frequency. So we would expect this number right here to be less than 1, because it's going to end up being multiplied by 297 and slightly decrease the frequency observed by the observer. Now, the opposite is true of the car. The car is approaching the observer, so it's trying to push those sound waves onto the observer with even more frequency than as if the car was just standing still. So the effect of the car moving toward the observer will increase the frequency. So we would expect this calculation to be greater than 1, right? So it's good to approach this kind of just thinking, you know, what's a reasonable value to get. So the plus or the minus, you can memorize it. But it's good to kind of just understand numerators and denominators and understand like what makes sense. So let's here are my notes that I used to cheat. Let's move those out of the way and pretend that I didn't even need notes because I'm a teacher. Teachers need notes, people. Even teachers need notes. Well, some of us do. Some of us mortals. So I've got this expression here. So here we go. Let's check it out. We've got velocity of the wave, which is, I think I calculated to be 343.8 meters per second. So I'm just substituting. And then I've got plus or minus divided by 343.8 meters per second. Now, I know that I need a value less than 1 because the observer is moving away from the sound, which is going to decrease the frequency, right? The frequency with which those waves are striking the observer. You're running away from those sound waves. So I know that it's going to be a minus sign because that is going to decrease my numerator. And if I decrease my numerator, I'm going to decrease the overall value of this expression. So let's go ahead and calculate it real quick. We've got 343.8 minus 20, and then I'm going to take that and divide by 343.8, and I get about 0.942, 0.942 4, 2. So that's my factor, and it's less than 1. So I think that makes sense. So then I'm going to come over here to this expression and say 343.8 meters per second. That's the velocity of the wave, divided by 343.8 meters per second. Okay, here we go again. Plus or minus the velocity of the source. That's Vs, the velocity of the source. Well, the source is moving toward the observer, right? And that is going to cause the sound waves to be absorbed more frequently. So we've got to get a value greater than 1. Well, to get a value greater than 1, the denominator would have to be less than the numerator, right? The numerator's got to be bigger to get a value greater than 1. So we're going to have to use subtraction here, and it's at 31.0 meters per second. So this is going to guarantee that my denominator is smaller, therefore I will get a ratio greater than 1. So let's check it out. 343.8 minus the difference between those in the denominator is 312.8, so divided by 312.8, and I got 1.099, and that's a factor greater than 1, so that sounds good, that checks out. So remember, this needed to be greater than 1, and this value needed to be less than 1. So now let's just put it all together. So the frequency of the observer is going to be Fs times the first factor times the second factor. So this is the fact that the observer is running away, and this is the fact that the car is, or the source. Sorry, I shouldn't say car. I should say the source. The source is approaching, and then I got 0.942 and 1.099, and my Fs value was 297. So 297 hertz times 0.942 times 1.099, and that gives me, let's check it out, times 0.942 times 297. I got 307.5. So we'll just round that up to 308 hertz. So that is the frequency, the sound frequency of the observer. I want to say observed by the observer, but that doesn't sound right. Now, if my explanation didn't quite make sense, you can always use these notes right here in terms of the plus or minus sign. So for this expression right here, let's zoom in a little bit. For this expression right here, where the source is moving, it says the minus sign is used for motion toward the observer. So you're going to use a minus sign when they're getting closer together, and the plus sign for motion away from the observer when they're getting farther apart. And then for this expression right here, this calculation, right, it says here the plus sign is used for motion towards the source, and the minus sign is used for motion away from the source. So I get confused trying to memorize which is which, so for me it just makes sense to kind of think about whether or not the factor should be greater than 1 or less than 1, just based on the logic, but that may or may not be helpful.